Okay, problem set 26. It starts off by asking us to evaluate this integral here. First off, I recognize that this is the same thing as just this coefficient times 1 over x. And I know that the integral of 1 over x is the natural log of x, right? Because we know these derivatives. So going backwards from this, I'm going to get this. So it's going to be this coefficient times that natural log of x. And then we need to evaluate it on these bounds. So it's going to be negative 1/4 times the natural log of x from 1/4, or from 1/9 to 1/4. So it's going to be this. And then minus, that minus a negative turns into a plus. 1/4 natural log of 1/9. And we could leave it there, but I would like to simplify this, of course, based on our logarithm rules. I know that when we add two logarithms, that's the same as having multiplication on the inside of that integral. And I believe, give me a moment. I've thrown myself off a little bit. Trying to remember, I haven't dealt with log rules in a long time. So this is the same as natural log to 1/4 to the negative 1/4 plus natural log of 1/9 to the positive 1/4, and then I can rewrite that as those exponents throw it off, huh? Okay. Well, in this case, I think I'm going to leave it as it is, actually. If this wasn't negative, I'd be less confused. But we're going to leave it as that. That's our answer that you could plug that into a calculator for a numeric result if you need to. For number 2, we're given that f of x equals this function here. We first want to find the domain. So we need to recognize two things. First of all of this is inside a natural log, and within that we also have a radical, a square root. So first of all, I recognize just from my square root that this inside can never be less than 0, right? Because having a negative inside my square root is undefined. We can't have that. So I see that this is going to equal 0. So x squared minus 64 equals 0 when x is plus or minus 8. Actually, because of that x squared, so going bigger than 8 or smaller than negative 8 is always going to be okay, right? Because if I have 9 squared, that's going to be 81 minus 64, that's okay. If I have negative 9 squared, that's still going to be 81 minus 64, that's okay. But the area that we can't have is between positive 8 and negative 8. Because, say, for example, it equals x is positive 4. Then I'm going to have 16 minus 64 inside my square root. That doesn't work because that ends up being negative 48 inside that square root. Same thing if I have maybe like a negative 4 squared, right? That's still going to be 16 minus 64, which is then negative 48. And again, we cannot have that. So I know that x has to be greater than or equal to 8. And it has to be less than or equal to negative 8, just based on that radical alone. Now we have to consider that natural log. Oops. Didn't mean to erase that. Now I have to consider the natural log. And the thing with natural logs is that we know that they can never equal 0. They can be any decimal above 0, but they can never equal 0. And they can never have a negative number in them either. Which is why oftentimes when we take the integral of something in its natural log, we actually we do want to be careful. If I have natural log of x, I typically don't want to write it like this when it's like an integral of something. I instead want to write it with an absolute value. Because if at any point x is negative, that would be undefined in a natural log without that absolute value. So now we need to see when this entire interior turns into 0 or a negative number. So I'm first going to make a note of what we found already up here, because I am going to erase it right here for now. And instead I'm going to take the interior of that natural log and I'm going to set it equal to 0 so we can see, sorry, so we can see when that happens. Okay, I can subtract x from both sides, and then I get this equals a negative x. If I square both sides, I get x squared minus 64 equals, well, it's going to be an x squared, or a negative x squared, which is the same thing. And then, I'm just going to get negative 64 equals 0, which doesn't work, which means there's no solutions to this. So there's no point when this interior equals 0. So it's safe to say that it is at no point going to be undefined because, yeah, and we might check that actually. So let's try plugging in some values just to make sure that this is positive generally, and it should be just because that addition there. But let's try, because I can't help but feel like I might have messed that up just because I'm thinking like if I plug in maybe like a negative 20, right? That's going to be natural log of negative 20 plus, well, negative 20 squared is going to be 400 minus 64. And this square root is obviously going to be less than 20. So wouldn't, uh-oh. I might have tried to solve for zeros incorrectly. Okay. That is a concern. So let's think about if I plug in a negative 8, in this case, if I plug in a negative 8, that's going to be negative 8. I'm just kind of double checking this extra part of our domain there. So if I plug in a negative 8, that's going to be negative 8 plus 0, which is obviously not okay. If I plug in and if I plug in a negative 9, same thing. And obviously I can't plug in anything bigger than negative 8 unless it's also bigger than positive 8 because that doesn't work. So looking at this, anything in those negatives basically is not going to work for us. So we can't include that. So our domain is just going to be that x is greater than or equal to 8, which I would write in interval notation like so. Now we also want to find the derivative of this function, which we very well could have done first. But so remember that the derivative, I'm first going to write the derivative of a logarithm, just any log. So derivative of a log is going to be the derivative of its interior times its interior, or divided by the interior times the natural log of its base, which means that the derivative of a natural log, which is a log with a base of e, is going to be whatever the derivative of the inside is, divided by the inside times the natural log of e, which is just 1. So it just looks like that, which we often end up just writing as 1 over x, but it's important to remember that we multiply it by the derivative of that inside because that's an application of our chain rule. And it's just helpful for us to not forget that. So in this case, the derivative is going to be the derivative of this inside just over top that right there. So now we need to figure out what the derivative of x plus the square root of x minus 64 is. Well, I can rewrite that square root like so. I like to rewrite it so that we can use that power rule. We are going to have to use chain rule here, so I'm going to write that my outside term is something to the 1/2 power, and then my inside term is that x squared minus 64. The derivative of my outside term is going to be the derivative of my inside term times 1/2, because bring down that power, subtract 1 from the power, which I could then rewrite as this over that. Okay, now I take the derivative of that inside, which is going to be just 2x. So I'm going to get 2x over 2 times the original term. Those 2's are going to cancel out. It's just going to be x over the inside of that, so 1/2. So I'm going to like so. So that's the derivative of this part, and of course the derivative of x is just 1. So that derivative is going to be 1 plus this here. And we could rationalize that. I'm not going to worry about it right now, though. So remember, once again, the derivative of that natural log is going to be the derivative of the inside divided by the inside, which tells us that our derivative is going to look something like this. Actually, I am going to keep writing it with that 1/2 power, just in case there is some simplifying we can do here, because there might be. Okay, so that's our derivative. Obviously, that's really ugly. We don't like that. We would like to simplify that as much as possible if we can. And I could be wrong, but I'm going to take a little bit of a leap of faith here, and I'm going to give this a common denominator so I can combine this top part into a single fraction, so that my complex fraction is just a little bit clearer. So of course it means multiplying this 1 by this over itself, which is going to get me x squared minus 64 to the 1/2 plus x, because I'm now combining the numerators, all over this right there. And that's all over this plus this here, which, interestingly enough, this is just this, but of course with our terms flipped, which means that if I'm dividing this fraction by this, I could rewrite that to make it a little bit clearer. And I'm going to rewrite it just to make it a little bit clearer what's happening here when I cancel these out. So dividing by this is the same as multiplying by 1 over that. And because this and this are the same thing, we've just got those terms flipped left to right. I see that those are going to cancel out, and I'm just going to be left with 1 over this here. And boom, that's going to be our derivative. And I am going to leave it like that because I honestly just don't feel like rationalizing. Sorry about that. But that's our derivative there. Next up, we want to evaluate this next integral here, which is an indefinite integral, but there's a lot happening there. It looks like we might want to use some U-substitution. And the reason that I say that is because I see I've got an x to the 5th down there and an x to the 4th, which I know is going to be part of that derivative. So I can see pretty clearly if I set my u value to this entire bottom term, then that means that my du value, which is the derivative of this, is going to be, well, that goes away, and I get negative 5 x to the 4th because of that power rule. which makes it pretty easy to substitute, right? So I'm just going to divide off that -5. So I get -1/5 du equals x to the 4th dx, which makes my substitution really, really easy, because now this integral looks something like this, right? Because I've got that -1/5 times 1 over u, because this is going to be my u value there. And that's that. And so again, this is pretty much the same as that first integral up top, where I've just got this coefficient and the other part is 1 over u. So that integral is going to be -1/5 natural log of u. And now I just have to plug back in my u value. So it's going to be -1/5 natural log of 7 minus x to the 5th. Oh, plus c, because it is an indefinite integral. Don't forget that plus c. It is very important. I wonder if I can just... There we go. Okay, next up is another one that looks like we probably have to use some U-substitution, because I'm not really sure how else we do it otherwise. This one's a little bit less clear, but I do see that I've got this natural log of c to the power of 8. So I'm going to go ahead and try out making u that natural log of c, and we'll just kind of see where that goes. Typically, making our u value the more complex, or like the more advanced, I don't know the right word there, but like the more complex term that we can find, typically is the right move in my experience, just because you often aren't able to make things more complicated when taking the derivative, but you can generally make them simpler. That being said, it's not always the case. That's not always the case. And sometimes you just have to do a lot of manipulation with your values, and it's not always very fun. But in this case, I see taking the derivative of natural log of c, it's going to be 1 over c dc, which that actually works kind of perfectly, because that means that we have a u to the power of 8. And then this goes away completely because we're substituting it for our du. So our integral in this case turns out to be just that. And then taking that integral is going to be 1/9 u to the 9th, because we're undoing that power rule, plus c, and then we just plug back in that u value, so we're going to get 1/9, and this is a capital C, and this is a lowercase c, so they are separate things. So it's 1/9 natural log of c to the 9th plus c. There we go. Number 5 is a similar one to number 2. So they're giving us this function, which is a natural log function, and they want us to find the domain and the derivative. Once again, I'm going to start off by finding the domain. So if f of x equals a natural log of this here, well then, of course, I know a few things to be true. First of all, just looking at this radical, I see there's a fraction within my radical. I know that x can never equal 4, because if x equals 4, I've got a 0 in this denominator, and that's undefined. That being said, let's see, x can equal 5, because it would just be a 0 in the numerator, but if x is less than 5, then we'd have a negative up top, but it can't be 4, and anywhere between 4 and 5 would mean a negative up top, but a positive on the bottom. Looking at it being maybe less than 4, though, say, for example, I plug in x equals 3. That would be 3 minus 5, which is -2, 3 minus 4, which is -1, which just turns into 2. And the square root of 2, that's valid. So that tells me that we're on the right track. So I know from this that x cannot equal 4, and x cannot be greater than 4. or it cannot be between 4 and 5 rather, but it can be less than 4. X can also be greater than or equal to 5, just looking at this radical right now. So this is what we know so far. Now we need to take that into the context of our natural log. Like we said before, a natural log can never equal 0. So even though we can have a 0 inside of our radical and in that numerator, we can't, that would make this entire interior of our natural log 0, which would be undefined. So x cannot ever equal 5, but it can be greater than 5. And of course, taking the square root of something, it'll never be negative. So this is our domain here, which means it can be less than 4. So it goes from negative infinity up to 4, and then it goes from 5 up to positive infinity to write that it's greater than. On to our derivative now. Again, the derivative of natural log is going to be the derivative of the inside over the inside. So now I need to figure out what the derivative of that is, and that's a little tricky, but not the worst. Trying to figure out what derivative method I want to use for this. I'll say we'll start off with chain rule. So we're going to write it like this. Or, actually, I could split up that natural log, actually. And I just might. Let's see what happens if I split it up. So, of course, all of this in the radical is the same as the radical up top times, or I guess divided by the radical on the bottom. So I could rewrite that as this. Because remember, subtracting a natural log is the same as dividing the interiors of them. So I could rewrite it like that, which means now taking the derivative is taking the derivative of each piece. Well, that makes it a lot easier, so I don't have to use that quotient rule. Instead, I've just got chain rule. So I'm going to drop that exponent in front. The derivative of x minus 5 is just 1, so it doesn't change much. And it's the interior. Subtract 1 from the exponent. Okay, so that's the derivative of that part. So the derivative of this natural log is this over this, and then minus, same deal here. So this is the same as x minus 4 to the negative, or to the power of 1/2. Bring that 1/2 in front. The derivative of x minus 4 is just 1, so it doesn't change anything. Subtract 1 from the exponent. Remember, the derivative is of a natural log, sort of the inside over the inside. So now it is this, and we can simplify from there. So ignoring our coefficients there, I see that these are the same, and I can actually move this down there with that, which will mean that I'm adding those exponents. So that's going to be, I can actually rewrite that as 1, and I can bring that 2 in the bottom. And now, because this is saying it belongs in the bottom, because of that negative exponent, I'm going to move this down here, which means that I have essentially this term times itself, which just undoes that square root and just makes it that. Same thing is going to happen here. Oops, didn't mean for that to be what it undid, but okay. Same thing happens here. So this is what we get. And I'm going to distribute that too, actually. That's going to be That should not be a 5, that should be a 4. Sorry about that, but it's because we're doing that one. Okay. And just gonna find like terms, combine those there, so it's gonna be 2x minus 8 minus 2x plus 10 over, and then whatever this multiplied together is. You of course don't have to do quite all of this work. You probably could have left it, honestly, maybe up here. Probably could leave it there and type that in. I just like to get us as simplified as we can because that's good practice. I know our exams we tend to need to simplify a lot. It's going to be 4x squared minus 16, 20, 36x, I believe, plus 80 and that's going to be, that cancels, so I get 2 over that. Oh, and I can actually factor out and cancel that too. And that's how I'm going to leave that. Oops, that goes up here. Let me know if I messed up anything in the comments, because I did go through that pretty fast. So there's a chance that I may have made a mistake or two. Also very tired. But we've just got 2 questions left. Number 6 is a new type of problem. We're given this frankly atrocious radical and told to use logarithmic differentiation to solve for the derivative of f of x. Logarithmic differentiation is just taking the natural log of both sides and then implicitly differentiating it. And then just kind of manipulating it from there. It's, I won't lie, a bit of a pain in the ass. But let's go ahead and give that a try. So, gonna need probably a lot of space for this one. So f of x equals the 7th root of this over this here. If I take the natural log of both sides, I'm going to get that the natural log of f of x equals the natural log of this 7th root of all of this in here. And the reason that this is helpful is because of the way that we're able to manipulate our logs based on our log rules. So remember how I kind of broke up that log in the other one into one log minus the other because of that division? We're going to be doing a lot of that here. So the first thing I see, so right now we're going to ignore this left side. Don't really care about it yet. So we're just going to ignore it right now. So what happens is I see that this is all inside a square root, which tells me that it's to the power, or not a square root, sorry, but a radical, a 7th root, which tells me that it's to the power of 1/7. So I can rewrite that. Any powers that I have, I can rewrite as a coefficient in front of my log. So I can write that as 1/7 natural log of all of this. From there, it's just more breaking it down. So from there, I can split it up into this top part minus this bottom part. So it's going to be 1/7 natural log of, I'm going to keep that 1/7 on the outside of all of it. Just take that as a big old coefficient just so we don't lose anything. So I'm turning it now into just this top part divided by this. And remember, when we're dividing the insides of our logs, I can split that up into this, the log of this top part minus the log of this bottom part. And if you're confused as to how that works, I don't really know what to tell you. That's just the log rules that we know from probably pre-calculus, I think. So then I can write it like this. Okay. So this is what we've got now. Oops, sorry. And I'm going to break this part up. Because these are multiplied here, I can break this up into two logs added to each other. So it's going to be the log of this first one plus the log of this second one. I suppose I didn't need those extra parentheses for that one, actually. Minus the log of this here that we already did, or that we already pulled out, rather. Okay. And now, because I've got a power here and a power here, oops, I put that one inside my parentheses by accident. That should be out there. Again, I can pull that out in front as a coefficient as well. So this becomes 5 natural log of x minus 3 plus natural log of 3x plus 1 minus 2 natural log of 9x minus 4, and I believe that's all we can do now. From this point, remember that this is all equal to the natural log of f of x. Now, we take the derivative. But it's a lot simpler now because we broke up this log. We broke up the natural log, and remember, the derivative of a natural log is the derivative of its interior over the original interior. Which means that if I take the derivative of natural log of f of x, well, that's going to be the derivative of f of x divided by the original f of x, because it's the derivative of my interior divided by my interior. So this is what we have now. That might not seem helpful, but it very much is. Now, we take the derivative of all of this. We can keep this coefficient out there because it's not a super big deal. I know the derivative of x minus 3 is 1, and that's times 5, so it's going to be 5 over the interior. Now plus, well, there's no coefficient here. The derivative of this is going to be 3, because the derivative of 3x is 3, over 3x plus 1. Now minus, I've got a 2 times the derivative of that interior is 9, so that's 18 over the original interior. And now we're getting somewhere. On the homework, I think it just has you essentially kind of set it up like this, or pretty close to it. I think actually you will have to distribute this to all of them for plugging things on the homework. But for comprehension's sake, the derivative of this is now, if I want to just have f prime of x, I just have to multiply both sides by that original f of x. And while that may initially feel useless, because it's just f of x, how is that helpful? We know what f of x is already. We were given that function. This is just a placeholder. So I could, theoretically, or not theoretically, literally, rewrite this as all of this. Actually, I'm gonna distribute this out. So it's gonna be that. I'll fully distribute it out, actually. So it's going to be 7x minus 21 plus 3, 21x plus 7 minus 18, 63x minus 28, all times that original function of the 7th root of all of this. Oops. So this is the derivative of f of x. And it's not a pretty one. We definitely could combine these fractions, but that's also not going to be pretty. And I don't think we need to for the homework. So I'm just going to leave it like this. I'm not going to rewrite it up there because it's all there. And now for our final problem. God, I hope that made sense because that was a tricky one. Now for our final problem, we're given this function here. So f of x equals the natural log of x squared plus 4. And we first want to find our y-intercept. Well, our y-intercept is whenever x equals 0. If x equals 0, then f of x is the natural log of 4. So our y-intercept is 0, comma, natural log of 4. You could type that into your calculator for a more numeric value, but I believe the homework will accept that, and that is the most exact. Now, we want to know our extreme points, any asymptotes, and on what intervals it is increasing and concave up. Those are separate intervals it's asking for, which means that we have to take at least the first derivative and probably that second derivative. So taking that first derivative, I'm going to erase that. Once again, it's the derivative of our inside divided by our inside. So derivative of x squared plus 4 is just 2x. And then it's divided by that. Taking that second derivative, however, is a little bit trickier because now it's not a derivative of log, it's just using quotient rule. So knowing that, we have our low d high minus high d low over low low. So it's going to be 2 times x squared plus 4, because that's the derivative of our top times our bottom, minus our top term times the derivative of our bottom, which is our top term, funnily enough, over our bottom term squared, and then of course distribute and combine like terms. So it's 2x squared plus 8 minus 4x squared over all of that, which is then negative 2x squared plus 8 over x squared plus 4 squared. And that's how I'm going to leave that for now. So now that we know all those derivatives, we first want our extreme points, which means we need our critical points, because our extreme points are maximums and minimums, or relative maximums and minimums in this case, because it's not on a closed interval. So first find our critical point. So I want to know when that first derivative is equal to 0. I see that it is equal to 0 when x equals 0, and that it is never undefined, because that denominator can never equal 0, because no matter what I plug in there, it's going to be positive, and it's adding a positive. So our only critical point is x equals 0. Now, just because we are going to want to know what intervals it's concave up, I am going to also check for inflection points. So let's see. I am going to factor out that -2 actually, so it's going to be that, and that's just factoring out the -2 right there, just to make it a little bit easier on myself to figure out when it might equal 0. Once again, it's never undefined because of that denominator. And now I see that this is going to equal 0 whenever this part equals 0. So it's x squared minus 4 equals 0, or x squared equals 4, which means x is positive or -2. So now we need to take a look at our intervals. So I know I've got -infinity up to -2, -2 up to 0, which is a critical point, 0 up to +2, which is another inflection point, and 2 up to infinity. Now, we'll go ahead and do that first derivative test to figure out where it's increasing and decreasing. So I'll try plugging in a -3. That's going to get me a negative up top and a positive on the bottom. So it's negative or decreasing. Oops. So it's decreasing there. If I plug in a -1, get that same thing and get a negative up top and a positive on the bottom. So it's still decreasing. Plug in a +1 though, and suddenly I have a positive up top and a positive on the bottom. So it is now increasing, and we'll see the same thing. Oops. Sorry. Here I've got positive up top, positive bottom, increasing. So I know it's increasing on this interval, so I can go ahead and write that. So from 0, I can actually write that as an inclusive interval, I believe. So from 0 up to infinity is where it's increasing. And now we want to figure out the concavity. So now I'll do a second derivative test with probably those same points. Plugging in, and I do want to keep that factored. It's just a little bit easier for me to work with in my head. Okay, so plugging in a -3 here, I'm going to get 9 minus 4 is a +5. So I have a -2 outside times a positive over a positive, which means it's an overall negative or concave down. Plugging in a -1, I have that -2 on the outside. 1 minus 4 is -3. So that's positive overall because those negatives cancel out. It is concave up. Plugging in a +1, same deal happens. It is concave up. And then plug in a +3, and I've got negative on the outside, positive on the inside, positive on the bottom, and it is concave down because that turns into a negative overall. So it's concave up right here. So non-inclusive from -2 to 2. That also tells me, looking at this, I'm decreasing all the way until x equals 0, and then I'm increasing. So while I don't have any relative minimums, I do have a relative while I don't have any relative maximums, I do have a relative minimum at x equals 0, which also happens to be my y-intercept, so we already know what y value that is. Now all that's left is figuring out asymptotes. If we know anything about our natural log, we know that there are no horizontal asymptotes. Or, hold on. Let me just double check that I'm not mixing that up. I always mix up my asymptotes. Okay. Right, so there's never so logarithms, including natural logarithms, do not ever have any horizontal asymptotes. So horizontal asymptotes are none. In terms of not positive asymptotes, vertical asymptote, again, we know that the interior of our natural log can never equal 0. So I know that I'm going to have a vertical asymptote whenever that interior equals 0, because it will be undefined there, and that's not a hole, that's an asymptote. Which in this case, since that's x squared plus 4, if I set that equal to 0, I'm going to get x squared equals -4, which means x equals plus or minus the square root of -4, but we can't have a square root of -4, which means that this doesn't exist, which means that there are no vertical asymptotes. So in this case, there are no horizontal nor vertical asymptotes. And that's it for this homework. This was only 7 questions, but as you can see, some of them were pretty lengthy. I hope that this all made sense, and I hope that this was helpful. Thank you for watching.